If you've worked on a large-scale system before, you may be familiar with needing to understand what's going on in that system when things go south, or what weird behaviors users are doing with your system. Facebook built a system called Scuba, which handles that use case, and many Facebook employees have really loved the Scuba tool and been wondering what exists out there that's similar to Scuba. Or maybe you've used something like ClickHouse to do data analytics, but you've been curious how that might apply to doing system analytics for observability rather than just doing big data analysis for your BI warehouse. So Honeycomb is a developer tools startup that was founded by some Facebook alumni to enable development teams to achieve better observability, to help them figure out what's going on inside of their production systems very quickly. So you may be familiar with monitoring, which is a mechanism for asking predetermined questions to do right-time aggregation, to create metrics, and to be able to answer questions based off of those pre-aggregated metrics very, very quickly. In contrast, observability, or maybe this next generation of monitoring, however you prefer to look at it, is a mechanism of doing read-time aggregation. So not doing any form of pre-aggregation, but instead making any query that you want to run across your data as quick as possible so that you can figure out what's broken about your systems or what your users are doing. So in service of that objective, at Honeycomb, we built Retriever, which is a distributed columnar store for doing real-time event aggregation across traces and log spans. So Retriever, this is, by the way, my golden retriever. So Retriever is a data store that enables kind of that rapid resolution of what people are asking for in real time. So what do we mean by real time? Well, we mean that you need to be able to answer any question that you have to kind of drill down into your hypothesis and do arbitrary investigation as quickly as possible. 100 milliseconds is great. 1 second is okay. But if it gets any longer than taking a sip of your coffee, maybe you have to go and make a new cup of coffee. Maybe you need to go and grind your own coffee beans. That's going to slow down your developer experience and drop you out of that state of flow when you really, really need to be debugging an incident or resolving that bug report. So Retriever's predecessor, Scuba, was built at Facebook to solve many of these challenges. And it operated strictly in memory and enabled people to fill in fields like what are they looking for, what are they grouping by, what graphics, what aggregations to apply, and enabled people to run that across hundreds of Facebook machines that were storing all of that data in a rolling circular buffer in memory. So Honeycomb's founders worked at Parse, which was acquired by Facebook, and they experienced for the first time the power of Scuba because it helped them solve problems that they were having with multi-tenancy inside of Parse, where they had high cardinality and high dimensionality of their users, and they couldn't necessarily figure out before Scuba which user was causing the problem, and therefore get to the bottom of it. So when they left Facebook, they wound up starting this company called Honeycomb in order to bring the power of Scuba to the masses and not just keep it locked up inside of Facebook. So Honeycomb has evolved, starting from being very, very similar in many ways to Scuba UI, and kind of has made itself easier to use so that it's not just usable by very, very smart Facebook or Meta engineers, but enables you to also learn from your colleagues and kind of clone their queries and fork them, and to also offer a more intuitive experience around being able to think about how are we running things in terms of almost a SQL query with completions and with the ability to very rapidly iterate on the query that you're running and give you the answers in familiar formats that you expect, such as, for instance, being able to visualize data as time series, as trace waterfalls, and even with some tricks that Scuba didn't do, like surfacing which dimensions are the most relevant to your query rather than you having to know in advance which dimensions you want to query on. So hi, I'm Fong-Jones, and I've been working at Honeycomb for the past 5.5 years, and I'm currently our field CTO. And joining me later for Q&A will be Ben Hartshorne, who is an early Honeycomb employee who worked at Parse before working at Honeycomb. And he's a principal software engineer here, working on all aspects of our ingest and our storage system. So today we're going to talk about 4 things. We've already talked about the problem space of observability and kind of some of the background on why a system like Scuba or Retriever might be useful. In the rest of this talk, we're going to talk about how we scaled out the retriever backend to handle much larger volumes of data than Scuba ever was able to handle, how we've solved some of the challenges around durability, and finally, how we've implemented some new features on top of the data storage engine. So let's have a little bit of a brief with Scuba's design, just in case you aren't familiar with it. So the Scuba system architecture involves having data streaming in from multiple data sources. It uses a 3-tier aggregation layer in order to run queries against that data stored in memory. And then it offers a web UI, a SQL interface, and a mechanism of running alerts or triggers against it. So these were capabilities that we extensively borrowed from Spiritually in building Retriever. In particular, this is what the aggregation workflow looks like at Scuba, where with Scuba, there's the root node that is running the initial query and then farming it off to intermediate aggregators. And then the intermediate aggregators then work with the data that's stored on individual leaves to then return the data from those 3 tiers. So with Honeycomb, we needed to reproduce the data ingest layer, which we call Shepherd. We have persistence in the form of using Kafka as our message bus. And then Retriever is one of the several different consumers of that data that performs the indexing of the data and the separation of it by data type. And by the way, yes, all of our services are in fact named after dogs. So how does Retriever actually store this data and make it lightning fast? Well, the primary thing is that we're kind of selective about the data that we ingest. We want data to be formatted in terms of having distinct fields, arbitrarily wide fields. So as many potential fields as you would like to have, and as many distinct values of those fields, high cardinality, as you would like to have. So the first optimization that we did compared to Scuba is that instead of storing the data in memory, we started persisting the data to NVMe local storage on AWS EC2 nodes. This is not nearly as expensive as running it on Elastic Block Store or EBS, but it still achieves a much greater economy of scale because you're able to have the lower cost of solid-state flash drives rather than needing to pay for very, very expensive, very, very low latency memory. There is still a trade-off here in that if you delete one of these nodes, the data on the local NVMe is gone, but because of the cost savings, it's very well worth it. So we farm out the data by having each ingest node select a random Kafka partition to write the data to, and then have a retriever per Kafka partition consuming off of that topic and writing the data to local NVMe storage. And then initially, we adopted a 2-tier storage system, where the query comes into a leader node, and then it performs the query across each partition with a relevant data set. And each retriever is doing the local aggregation off of the data stored in its local storage, and then returns the data to the leader, which then does a second layer of aggregation and returns the result. And we're efficient about querying data in the same way that Scuba is, in terms of using the columnar storage format, in which data is separated per key or per column, so that we're storing all of the trace IDs together, all of the trace span names together, all of the build IDs together. And the reasoning behind this is that it enables us to only scan the data that's relevant to the user's specific query. If someone is asking only about the user ID, we can filter only the user ID and discard extraneous data, such as, for instance, the user's locale or the user's mobile phone version. The other optimization that we do, and also this is something that Scuba did, is that we segment data by the timestamp of its arrival, so that we have kind of the idea of there is a segment that is broken up by the data that we received between 1 and 2 minutes ago, the data that we received between 30 seconds and 1 minute ago, and so on and so forth. And we're also recording for each segment the start and end timestamp, the highest time at which the event was generated, not received, and the lowest timestamp at which the event was generated. And this is in service of having each segment have a known time range. Why does this help us? Well, because if someone queries for data between 1 and 3 hours ago, I don't need to fetch the data from between 24 and 48 hours ago. I can just discard that for the purpose of this query and only focus on the segments that might have relevant data. So this has really enabled us to design for speed and scale. But it wasn't enough to help us scale out as we encountered more and more sophisticated and large customers. So the more data comes in, the faster the data expires off of that circular buffer. And indeed, this was a pain point that Scuba experienced at Facebook, more acutely because of memory. But even when we had terabytes of storage available to us on NVMe SSD, it meant that we are expiring data after hours or minutes rather than days. So in order to solve this, we decided that instead of deleting the data after it expired from the local circular buffer, that we would tier it off to S3. The logic being that data that is less recent is less likely to be accessed, or at least that we might need to access it less quickly. People might expect that a query against the most recent hour completes in seconds, whereas they might be willing to wait a minute or two to retrieve data from a month ago. So by doing this, we were able to store up to 60 days of data. Yay, this is great, right? So we were able to say, we're just going to use the same read path. We're going to keep the two-tier aggregation layer, and any retriever that needs to get data that's from S3 will pull it back down onto local storage and perform the query as normal. But there is a cost to this, which is that if you're running a 60-day query, suddenly it takes minutes and not seconds, as I was saying that we were optimizing for before. So we needed to get things back into the realm of taking a sip of your coffee. So the short answer here is that, yes, we could, of course, choose to install a bunch more EC2 nodes, dedicate them just to reading the data off of S3, but then we'd have to pay for those nodes all the time. This is kind of like my dog, right? Like when my dog wants to play, she'll get all of her toys out of the basket, but then when she's done, she just leaves them on the floor. And that's a little bit of a pain, right? Like you'd rather not have the toys on your floor all the time. You'd rather have them out only when the dog wants to play. So how can we get this in a compute sense? The answer is that the combination of AWS Lambda and AWS S3 allow us to arbitrarily scale out horizontally on demand only when people click the Run Query button inside of Honeycomb. So by solving this problem of having there be too much data for one retriever, we were able to essentially kind of reproduce the Scuba three-tier architecture, except for instead of having the leaf aggregation happen on individual servers or VMs, that third tier aggregation, the leaf tier aggregation, is happening on tens of thousands of concurrent Lambda workers that are all essentially stateless because they're able to fetch the data off of S3 rather than having to look at something on their local disk. And then we have the retrievers that are kind of storing the data on their local SSDs, process always the freshest data, but the older data can be processed in parallel at the same time. And that means that now we're back into the realm of being able to take a sip of coffee and your query is already answered by the time you're done. So by buying this compute in 1 millisecond units, this means that we're able to get this rapid response that our customers are delighted with. But there are some caveats, of course, to this scaling up. It's more expensive, the cold start time can cause some issues, and some of the queries never come back. Overall, though, it's enabled us to achieve petabyte scale, and that's kind of a miracle when you think about how much a petabyte of memory would cost, which is what it would have cost to do this with the conventional Scuba architecture. So this is one of our metrics tracking our bytes under management, and compressed, it's crossed 1 petabyte as of a month ago. So let's talk about some of those trade-offs now with making the engine fully serverless. Because Lambda is on-demand compute, but they don't necessarily expect you to be using it for batch data processing. They're expecting you to be using it to, run like a service through API gateway. So the first piece is the scaling up. What does it look like when you want to run more workers than AWS allows you to by default? So Amazon will return you a HTTP 429 result if you are asking for more concurrency than you're allowed. They will allow you to scale out your concurrency limit, but only if you have sustained load. So it used to be that you would have to run at your concurrency limit for 1 whole minute before they would increase it, but now it's 10 seconds. But for us, that still is a little bit too slow. So we've actually negotiated with Amazon to get a higher custom concurrency limit that enables us to burst to tens of thousands of concurrency and verify that we're actually getting that. And that if we're not getting that, to figure out, what's the bottleneck? Why are we not able to kick off that many Lambdas in parallel? So by kind of investigating the SDK limits, by talking to our AWS team, and by making sure that we're retrying requests that are throttled, we are able to benefit from that massive parallelism and run requests at scale. Cold starts. So yes, cold starts can be a little bit of a problem, but on the scale of a 1 to 2 second query, 50 milliseconds of startup time is really not that big of a deal. And in practice, we're actually able to measure how much time is spent in the instantiation of a new VM inside of Firecracker, how much time is spent inside of our main function, versus how long are our workers actually running. And also what we're able to see, which is pretty cool, is we're able to see the garbage collection life cycle of the lambdas. We can see that the kind of sum total of lambdas that are running and sleeping, and also how long it takes for them to be garbage collected. So you can see here that one user ran a number of queries against Honeycomb's backend, and it caused about 100,000 invocations per minute or so. But after we were done with those invokes, Amazon persisted those Lambda workers for about 10 minutes, and then it started killing them off very rapidly, bringing us back to our normal baseline levels. So it's really great that we have the tools to understand and manage our concurrency. But what about making sure that the requests are successful and that the latency is under control? Well, one problem is that while 90% of requests are able to return within 2.5 seconds, there is a very, very, very long tail when it comes to working with S3. So our functions wind up having a significant minority that wind up taking 5 minutes to come back or never coming back at all. So we just wind up killing off the worker that is not responsive and retrying. So we automatically retry the slowest 1% of requests. And because failures that occur within S3 or Lambda are usually transient, a retry of the same exact request will usually return very quickly. And therefore, we're able to return results within 10 seconds, even if individual workers take far longer than 10 seconds. Finally, there's the issue of cost. I think there are two dimensions to this. First of all, yes, Lambda is 3 to 4 times more expensive than EC2 per CPU millisecond. But the advantage of Lambda is that you get 100% utilization, that you're only paying for the milliseconds of CPU you actually use. If we were to actually run all of our concurrent workers on EC2, we'd be getting less than 5% utilization. So while it may look scary to have a bill for tens of thousands of dollars per day or per month, it winds up in practice working out cheaper for us, and even though it is expensive, we believe the benefit to user experience is well worth the cost, because that is our differentiation of being able to very quickly return results and not disrupt people's flow. The other thing is that storing the data on S3 does incur a cost every time you go to query it. So even if we were to make our Lambdas run 50% faster, we wouldn't necessarily achieve that much of a cost savings because of the fixed cost of querying S3 and the fixed cost of sending that payload enumerating the files to scan. So nothing really matters unless users are happy, and in our case, our users are developers, and we're willing to spend money in order to ensure they have a good experience. So next, now that we've talked about the issues with scaling, let's talk about durability. So Honeycomb's design is meant to persist data because we can't say, oops, we restarted the server, a third of your data is gone. It's very tricky, but we've managed to solve this by careful design and using good primitives. So we use Kafka to persist our data, which means that we're able to enqueue data at random from our ingest workers called shepherds, and then our retrievers are able to pull the data off of Kafka. So in order to do this, we're storing a backup of every indexing worker every hour to S3, and then that way you can always resume from Kafka from an S3 backup. But it's a very delicate failure overdance, and things can go wrong. For instance, if you lose a Kafka broker, then you need to change which leader you're talking to, and you need to re-replicate to ensure durability of the Kafka. So in this case, we need to test regularly whether we're able to do Kafka broker replacements. Similarly, if we lose a retriever node, we need to make sure that we're still serving requests. So in fact, we don't just run one copy of retriever per partition, we run 2. And that way, there's always one copy of retriever running to serve, even if its peer is broken. And we can restore durability in parallel by reading off of S3 and then playing back from Kafka. So how do we actually verify that this works? Well, the way that we do that is by restarting one server and one service at a time. And we monitor to make sure there's been no disruption to our users using our service level indicators and service level objectives. And should something go wrong, we've got really good observability into our node replacement processes, into our startup processes, and so forth. So in the event of the loss of a Kafka node, we fail over seamlessly to reading from the new leader. And in the case of having a restart, for instance, needing to do an upgrade of all of our retriever versions at once, because we like to deploy software to production every hour, whether it's a stateless service like Shepherd or ingest service, or a stateful service like retriever, we need to make sure that we're not restarting two nodes at the same time that are responsible for the same data. So enter our Kubernetes operator. So our Kubernetes operator is aware of availability zones and partitions to enable us to safely do restarts and upgrades, and also to make sure that data is spread across multiple availability zones. And it constantly reconciles to make sure that we remain in a safe state. And of course, yes, there's telemetry about that. So should we catastrophically lose a single AZ at a time, we should, in theory, be able to continue serving without a blip to our users, right? Well, one way of verifying this assumption is to actually continuously verify, to run destructive experiments, not just on one node, but on all of the nodes in an availability zone. So this is what we did recently. We recently used Amazon's fault injection service to not just test in production, but destroy in production on a Friday. So we were able to use fault injection service to take down simultaneously all of our EC2 nodes in US East 1A, and to verify that traffic continued to flow, and that when we did restore US East 1A, that we were able to watch all of our nodes re-replicate and catch up, even while their peers were still serving traffic. And eventually we had the full dual concurrency of two retrievers running for each partition, and therefore we were able to declare our mock incident over. So finally, let's talk about how we not just maintain stability, scalability, and durability, but also add features. So Honeycomb users have been asking for a long time for the ability to run queries not just across all of the fields on one span, but to run queries across all of the fields on all of the spans within a trace. So to be able to ask questions like, does the root span have a name of cart checkout? So in order to do this, we needed to make both retriever and shepherd aware of this idea of what is a trace, and making sure that all of the data for a single trace winds up on one retriever partition. So we needed to ensure that we are using consistent hashing to make sure that all of the spans for a single trace, regardless of which shepherd they arrive on, are sent to the same Kafka partition and therefore processed by the same retrievers, and therefore that they can be retrieved by the same retrievers and that you can run aggregations at read time on them. So we did this by modifying shepherd and retriever, and this was very much like changing the wheels on the race car while it was in flight, because we had users that needed to be able to continue sending data while we were rearranging their data for them. So if you're interested in learning more about how we do this, you can read Observability Engineering, which is our O'Reilly book, and Chapter 16 in particular talks about the inspiration of Retriever based off of Scuba and how we evolved it over time. And with that, I'll leave you with one last picture of a very happy dog, of my golden retriever, Flurry. Thank you very much, and I look forward to taking your questions alongside Ben in the break.